In this video, I want to take a look at the notion of directional derivatives. Now, we have the notion of partial derivatives, which for a function of x and y tell you the slopes in the x direction and the y direction. Right, so the partial with respect to x would be the derivative in the x direction, and the partial with respect to y is the derivative in the y direction. Now, what about all the other directions? How do I find the slope in those directions? Well, it turns out that the chain rule is going to allow us to do that. And here's how we do it. So suppose we want to know the slope of the graph of c equals f of xy at some particular point, x0, y0, in the direction of a unit vector, AB. Now I want to emphasize here that this is a unit vector, has length 1. The textbook that we're using this quarter always writes their unit vectors in this section as cosine theta, sine theta. So they picking theta equals 0 being the positive x-axis. And then they turn their angle counterclockwise, theta, and then they have the unit vector in that direction has an x component of cosine and a y component of sine. And so they just list it that way. I don't really care to do it that way right now. I want to just say AB, but notice that the square root of a squared plus b squared is equal to 1. This is a unit vector. Now, consider the path in the plane given by x0 plus at, comma y0 plus bt. So this is a vector function. At t equals 0, you're at the point x0, y0. And the derivative vector of this thing is, the derivative with respect to t, is a comma b, right? It's this, which we point out the length of that thing is equal to 1 because this was chosen as a unit vector. So the point is this is moving at unit speed. Right? Now, I have a picture here that shows the graph of a function and a curve on the plane. This happens to be moving, I don't know if this is the x direction. Yeah, it looks like this is the x direction at the moment. But let's click on this and make that be able to see this better. Okay. So I have this set up this way. Here's the point x0, y0. In this example, it's x is 1, y is a half, and then you plug that in to get the point up here on the surface. Okay. Then I've chosen a unit vector, which currently is drawn, headed off in some random direction here. And you can see the curve on the surface up above. And I have this so that I can slide, face is in the way here, hang on. So I've got this slider that allows me to change the direction of the unit vector. You can see it down below here. As I slide this around, you can see that that is changing. And the curve on the graph is always staying directly above that. I mean, it's a curve up there. It's a straight line down the xy plane. Because you're then mapping it up onto the surface, this becomes a curve. But and you can see that as you look in different directions, you have a different slope. Right? That here's the x direction, right about here. The y direction is there, right? And the question is, in any direction, what's the slope? How do we calculate it? Well, here we go. Because I've chosen a unit vector, my motion in the plane has length 1. It has speed 1, right? So 1 increment of the variable t corresponds to 1 unit of distance in whatever direction that is. So when I'm thinking about the derivative, I just want to know what's rise over run? How much rise is there for one step of run? And I don't care if that's one step of run in the x direction or in the y direction or in any other direction, as long as it's the same one step. Give me one bit of run, how much rise is there? Rise divided by run is the slope. Right? And so because I have a unit vector now, I'm going to say that dz dt, that is the change in the z component with respect to t, will be my slope in that direction. And again, this is hugely depending on this being a unit vector that I'm moving, because I want change in rise over change in horizontal distance. And what does the chain rule say? Well, the chain rule says, since z is a function of x and y, that you take the partial with respect to x multiplied by dx dt, and then take the partial with respect to y times dy dt. Well, we noticed above that dx dt was a and dy dt was b, and so this is just the partial with respect to x of the function times the x component of that unit vector plus the partial derivative with respect to y of the function times the y component of the unit vector, which I could write as a dot product. I don't think the book does at this point, but I want to point out I could write it this way. It's partial f comma partial y dotted with the unit vector AB. This vector out here with the two partials in it will be defined as the gradient in the next video, but for now we want to focus on the directional derivative. Okay. So I actually make the definition here and say, given a function, f of x, y, and a point, x0, y0 in the plane, and a unit vector, AB, notice that the unit vector, I didn't mention this before, but this has only two components, so I'm not looking up the slope or down the slope. This is just horizontal. There's no z component, so you're just looking in a direction in the xy plane, and then you're saying, if I move in that direction, what's the slope of the graph of this function above? And a couple note ways that this is notated. Some books, in fact the one we're using here in this course, denotes it d sub u of f, so the derivative in the direction of u of f, and then at x0, y0. I've also seen it, and actually this is the way I prefer to do it, is just f sub u, like we do f sub x for the slope in the x direction, or f sub y, the slope in the y direction. I think this f sub u is the slope in whatever u direction it is, right? Where u has to be a unit vector. And it's given by what we just calculated up here. Take the partial with respect to x, evaluated at the point x0, y0, times the x component of the unit vector, and then likewise partial with respect to y, evaluate x0, y0, times the y component of the unit vector. So to do an example, actually this example is the surface that we had in above. F of xy is sine x plus sine y, and I'm going to look at it at the point 1, 1/2, which is what the picture was, and we'll look at it again momentarily. The partial with respect to x is cos x, the partial with respect to y is cos y. If I evaluate those at the point I'm interested in, at 1/2, partial with respect to x is just cosine 1, which is about 0.5403. There's, of course, infinitely many more decimal places, but and fy at that point is cos of 1/2, and it's 0.8776. So now, with these two bits of information, I can find the slope in any direction at the point 1/2. So in particular, if I look at 1, 0 in that direction, well, that would be looking right down the x-axis, and what I get is this times the 1 plus that times the 0, which is just this. It's the partial with respect to x. So in the direction of the positive x-axis, directional derivative is the partial with respect to x. Likewise, in the direction 0, 1, which is in the direction of the y-axis, I get, no surprise maybe, the partial with respect to y, right? This part is gone, and this part is 1. Now, interestingly, if you take a look at the direction -1, 0, then we have that this partial derivative is this times -1 plus that times 0, which is minus. So this is an important point here. This is minus the partial with respect to x. In the direction of the x-axis, the slope was 0.5403. In the direction of the minus x-axis, the slope is minus 0.403. Does that make sense to you, that if it's going uphill on this side, it should be going downhill on that side? In fact, this will be the case every time, that if you know the directional derivative this way, then you just multiply by -1 to get the directional derivative that way. So likewise here, in the direction of 0, -1, we get minus the partial with respect to y. Let's go in some other direction here. This would be the direction 1 over radical 2, 1 over radical 2. Notice I didn't just say 1, 1, because that wouldn't be a unit vector. So I took 1, 1, and I divided by its length to get a unit vector in that direction. And so then I have that the directional derivative in that direction would be 0.5403 times 1 over radical 2 plus 0.8776 times 1 over radical 2, which is 1.0026, right? Going back to that picture, in the direction of, that would be pi over 4. So if I look in the direction of point, what's point? Yeah, it's about right there. So this is the slope in that direction, which of course is steeper than the slope in the x direction or the slope in the y direction. You're headed uphill faster. Is that the steepest slope possible? That's actually a question that's going to be answered by the next video and the discussion of the gradient. Okay. But for now, there's the notion of directional derivatives. You got to find the two partial derivatives and then essentially dot it with a unit vector in the direction that you're interested in.